Okay, first the obligatory financial disclosures. And what I'm going to be talking about is three classes of methods we've been working on for diagnosing and understanding the progression of glaucoma using the ISSOCT Widefield scans. And these range from a method that's very qualitative and that you could probably do at home today to one that we've only have 2 weeks experience with. All right, so first a little background on the Widefield report. This is the report here, and it's based on a single Widefield scan, which is 9 by 12 millimeters. And it has individual B scans. In the case of the Triton, it's 256, and in the case of the Maestro, it's 128. Here's one of the B scans. They tend to have very good resolution. And we're going to be looking at we're going to use the machine segmentation, and we're going to be looking at the ganglion cell plus the plexiform layer and the retinal nerve fiber layer. And from that, we produced this report. And just briefly, because I'll talk about some details of it later, but just briefly, that's retinal nerve fiber layer thickness in pseudo color. So it's based on that layer. And that's retinal ganglion cell layer thickness. So it's based on that layer. And we don't look at it for the retinal ganglion cell thickness, we look at a 6 by 6 millimeter portion of the scan centered on the fovea. That's a derived circle scan that's derived from this single scan. And it's presented in end-stin view. What that means is it's got the temporal region of the disc in the center, which means that your center of your visual field and the center of your retina or macula are in the center here. And then this is the traditional circumpapillary retinal nerve fiber layer thickness plot. I'll say more about these two probability plots, but we make two probability plots, sometimes called deviation plots. They're both in field view. One's based on the retinal nerve fiber layer thickness. One's based on the retinal ganglion cell thickness. And I'll come back to those. And we've validated this report and described it in a publication 2 years ago. All right, so that the new version of this report that just was released about a week or 2 weeks ago for the Maestro, and it will come at some point for the Triton, makes a modification. And the modification is we're going to take the scan after it's been scanned and take the angle, foveal disc angle here, and rotate it to the mean of healthy controls. And there are two reasons for doing this. One is, if you see here, right, it's getting rid of that artifact. So one reason for doing this is extreme head and eye rotation can cause artifacts, and this will correct it. And in some cases, it will correct some of the anatomical variations among us as well. The most important reason for doing it, for the purposes of this talk, and this talk is about progression, is that if you want to look at progression, you want to compare the report from time 1 to time 2, and you want them to be along the same angle. Right? All right, so that gets me to the first method here. The first method, for the old timers in the group, you'll remember flickering between fundus photos. This is the same thing. So you can flicker between these. Here's time 1 for this patient. Here is the same patient scanned 1.2 years later. And now we can flicker between the two. And the power of this approach is everything should agree. You know? So if this is getting bigger, well, then this should get bigger. And this is invading into the macula, therefore there should be something here, and so on. And then here's another example. Same thing, everything should agree. So the main point for the rest of the talk is this flicker method. You can see there's a lot of information here in these probability reports. If the scan is rotated to remove head and eye torsion. All right, so the second method I'm going to describe is a region of interest method. And the concept is very simple. This is a paper we published a couple of years ago. And if you have an eye like this, where you have local defect, it makes no sense to follow progression by averaging all of the retinal nerve fiber layer around the disc. you might as well define a region of interest and see if that's changing. That's the logic. And recently, Zi Wu, who was a postdoc in our lab, automated this and quantified it and corrected for age and various things. Here's a study we just finished. It's going to be presented by one of the students in the lab, Ashley Sun at ARVO. She converted the previous work to using the ISSOCT. And what you can do is you can manually mark it, or you can let the software mark it. So the software, for example, could define a region of interest by where it dips into the yellow and red, or if you wanted to manually mark it, then you might say, oh, maybe it started out life like this and you can do this. And then the software shows you the other regions that are involved, right? So, and you can just take the thickness and then it can be compared to baseline using traditional event-related or time-related techniques. So you can see here, the difference from time one to time two. Okay, again, what we found here for detecting progression of early glaucoma. By early glaucoma, I'm always going to mean a mean deviation on the 24-2 better than -6. So some of these subjects would be suspects in your hand, some would have early glaucoma. So in eyes with local damage, this region of interest approach was better measured than global thickness. And in eyes with widespread damage, we found that global thickness may do better. And that's not surprising. And at least at the moment, we're better off with the manual than the automated marking. All right, this gets me to the third class, and the one that is most interested in at the moment, is suppose you wanted to compare structure and function. Well, there's a simple way of doing that just uses flicker. So you could take, for example, here is the time 1 OCT, and here's the time 1 visual field, and you can flicker it. And if you look at the arrows, oops, sorry about that. If you look at the arrows here, you can see that the field and the OCT are changing. All right, but here's something I think brand new. But to tell you about what's brand new that we're working on, as I said, just over the last couple of weeks, I've got to tell you about something that's relatively new. And what's relatively new is a new method that we developed in the last 6, 7, 8 months for comparing local structure to local function. So let me tell you about the detection first. All right, and here are 2 ARVO presentations that are going to describe this. So we're going to use these probability maps now, and let me blow them up and show you how we're going to change them so they can be used. So first of all, this is in field view, so we're looking at the superior visual field, the inferior retina, and the little circles are the 10-2 points. The big circles are the 24-2 points. If it's filled, it means it's significant at 5% or better. So take a look. So take a look at this arrow here. That point's abnormal at 5%. That is the physical location of that point. And here it is on the ganglion cell. So this is ganglion cell probability map, retinal nerve fiber layer. Okay. Oops. Okay. There's a cluster here of abnormal points. I'll just point out, there's your cluster of abnormal field points, and they're here. So that's abnormal field. How are we going to define abnormal OCT? Well, this is a continuous probability map. Green means not significant, probability greater than 10%. Dark red is going to mean 0.1%. Red's about 1%, yellow's about 5%. All right? So what Manos in our lab has worked out is the best sensitivity specificity, or area under an ROC curve, for different criteria. So long story short, we're going to define an abnormal functional point by a visual field that's 5% or worse. We're going to define an abnormal structure by an OCT that's 10% or worse. And we're going to define an agreement of abnormal structure and abnormal function if either this plot or this plot has 2 points that agree. So let me show you. here's one point. That's the only point that agrees there quantitatively. Right? Here, however, you've got a whole bunch of these that agree. So this would be confirmation of structure and function going together. And so here's something that may surprise some of you. So I get to present the interesting stuff since it's my lab. And what we did was we looked at 53 eyes of early glaucoma, again, suspects or mean deviation. Well, I guess they weren't suspects. These were all definitely glaucoma based on the referring physician, but they all had 24-2s better than -6. And 45 controls. About 90% of these patient eyes, right? 90% of these patient eyes, all but 6 had structure-function agreement. So this is a point we've been pushing for a while. Local structure and local functional damage agree even in early glaucoma. It is just not true that structure comes way before function. All right, so the point here is, in general, structure and function agree if you use both 10-2s and 24-2s, and if you use retinal nerve fiber layer and retinal ganglion cell, both maps. All right, so here, and you compare local regions. Okay, so here now gets us to an automated method we've been playing with for progression. So as I said, this is only 2 weeks old, and I only have a preliminary data. So this is your detection maps, and this is now going to be progression on structure versus progression on function. This part of the map here is that much, this part is that much, so let's just get rid of everything else so you can see it clearly. All right, here's how you read this. If you have a filled-in visual field point, it is progressing at 10% or better. It is progressing at 10% or better. And if you have a red spot, it is progressing on the OCT at 10% or better, right? If you have both, that's structure-function agreement for progression. All right, so now look at this. So here's a cluster, for example. This is all based on the thickness map, by the way. And that would be there to there. Well, you can actually see it's changing, but you would never believe it if I didn't have this quantification, right? And then it goes from there to there, right? And then on the visual field, you're going from there to there. All right, so here's the ganglion cell map for the same patient. There's, again, a cluster of agreement, and you can see it's there to there. Well, you can see, you may or may not believe it if you only had that, right? And there to there. Here's the cool part. There is a cluster of agreement. That's now going from those two regions from here to here, right? And maybe you can sort of see why. And down here, we have structure and function progressing and agreeing, even though on structure, it did not show up as abnormal. So it didn't show up as abnormal, but it's abnormally increasing and agreeing with the field. And then here's the field. Okay, so that's what we've been working on. The principles involved here come from our work on detecting glaucoma, and in the shameless attempt to advertise our website, you can find lectures about the detection part of this on my website. And because I have young people in the lab, they even created this so that you could photograph it. Thank you.